Here's a look at how to approach Rogowski's problem on the Three Gorges Dam. I'm saying it's his problem because other people make different assumptions about the height. The height he's using is 185 meters, 200 meters at the bottom, 300 meters at the top, 55-degree angle. What's the fluid force? So remember, fluid force for a flat panel is density times gravity times the depth or height of the water above the place times the area. So what we're trying to do is we're trying to get a slice that would have all the same force, right? All the same density, all the same depth. And so what are we going to do here? We're going to, first off, just parameterize this height. Let's imagine this is height 0, this is height 185. You could make different assumptions about that, but we're going to slice up and down this piece. So I'm going to have my density times my gravity slice from 0 to 185. Then I have to have the height. Now, if you make this assumption, how deep is the water at this slice? Well, sort of the average depth is 185 minus y. Of course, if you parameterized it the opposite direction, you'd have something different there. Now, the challenging part here is figuring out the area of that piece. So let's call that the width of this piece, and this right here, the length of that piece, okay? And notice this isn't vertical. So if I had this side triangle, you've got 55 there. This is 185. We're kind of concerned about how long is the hypotenuse. So remember, sine of 55 degrees would be 185 over whatever this hypotenuse is. And so the hypotenuse would actually be 185 over sine 55, right? So that's equal to 185 divided by sine 55. And this L here, if you're thinking about that L, that's a similar triangle. I want to know how long that L is when I have a change in y over here. So if L is to y, the same as 185 over sine 55 is to 185, right? If I divide everything in sight, oops, that's a delta y, right? This is just two similar triangles. If I divide both of these by 185, right? If I reduce this, this just comes out to 1 over sine 55. And L is delta y over sine 55. What's that mean? It means for every jump in height, you get a larger jump in the length of this chunk, right? The hypotenuse is longer than the height change. So what are we going to do here? For this area, we need this, that's the length. We also need the width. So what am I going to do for the width? Well, the width, if you think about it, this is linear. When y is 0, the width is 2,000. When y is 185, the width is 3,000. So what's going to be the slope of the width? Well, the width is going to, the y-intercept is 2,000, right? 2,000 plus it adds 1,000 for each 185 meters we go up. So that's the equation for the width. So what are we going to get? We put both of those pieces together here, and we get for this, no, I'm really, all of the stuff in red is calculating that area, right? It's 2,000 plus 1,000 over 185 y, and then in limit, that dy down here becomes, that delta y becomes dy over sine 55, right? And so this is the integral we actually have to calculate. We usually make the assumption that the density of water is 1,000, that gravity is 9.8. We can pull that sine 55 out. Now we've got the integral from 0 to 185 of the product of these two terms. So notice 1,000 over 185. We can say that's divide both by 5. So negative 237ths y squared minus 1,000, right, we got minus 2,000 plus 1,000 y plus, let's see if we're multiplying those, we have 370,000. Lots of force here. dy, that integral's pretty straightforward. Right, so we get negative 200 over 37 times 3y squared minus 500, sorry, y to the third, gotta raise the power and divide by 3, y squared plus 370,000 y evaluated between 0 and, I don't know where that came from, 185 meters. I went ahead and calculated that out. You could plug it in as well as I could. 4.718 times 10 to the 11th newtons. That's the fluid force.